Every year, the world lays down over 1 billion tons of asphalt, the material that modern civilization would literally grind to a halt without. But few people know that every foot of road is the result of a complex alchemy of stone, fire, and oil. It all starts with an explosion in a quarry and ends with a hot, black mass steaming under the wheels of a roller. In this video, you'll see how asphalt is born, from blasting rock to the final roller that polishes a new road. And if you stick around to the end, you'll learn a secret that most drivers don't even know exists. Almost nothing goes to waste. That crushed old asphalt is then added to the new mix back at the plant. On average, new asphalt laid on our roads contains about 22% recycled material. The payoff here is huge, both economically and for the environment. First, it drastically cuts down on the need to quarry new stone and produce new bitumen, which saves natural resources and energy. Second, it makes the final product cheaper, saving billions of dollars from road maintenance budgets. So, every car trip you take is a journey on a complex piece of engineering that not only withstands massive loads, but is also a prime example of an industrial ecosystem where the old is constantly reborn into the new, closing the loop and making the country's infrastructure a little more sustainable. The story of asphalt doesn't start on the road. It starts in two completely different places. The first is a quarry. It's a massive wound on the face of the earth where rock is blasted out. It all begins with a loud explosion that shakes the ground for miles. Huge boulders break away from the rock face. Then, giant haul trucks with wheels taller than a person move in and haul these stone boulders to the primary crusher. This is a metal monster that crushes massive boulders into smaller chunks with its steel jaws and incredible force. But that's just the beginning. The stone then goes through a whole series of crushers and screens, giant vibrating sieves. The goal isn't just to crush the rock, but to carefully sort it by size. The result is entire mountains of clean, sorted stone, which we call aggregate. You've got everything here, from large, fist-sized rocks to fine crumbs and even dust, like sand. Each size is stored in its own separate pile. It's like in your kitchen, where you have flour, sugar, and salt, each ingredient separate, waiting for its turn. This is the skeleton of the future asphalt, making up 95% of its mass. The second place where asphalt is born is an oil refinery. When crude oil is processed into gasoline, diesel, jet fuel, and other light products, a thick, black, viscous substance is left at the very bottom of the distillation tower. This is bitumen. In its normal state, at room temperature, it's as hard as a rock. You can shatter it with a hammer. But if you heat it up, it becomes a liquid, like thick syrup. It's this property, being solid when cold and liquid when hot, that makes it the perfect glue for our stone skeleton. Bitumen is the soul of asphalt. It's black heart that holds everything together. Now, let's head over to the asphalt plant. This is where all the ingredients come together. From a distance, it looks like a complex tangled metal jungle. Tall silos, endless conveyor belts, pipes, tanks, and a central tower with smoke rising from it. It's a real factory that works like a single, well-oiled machine. Different sizes of aggregate are fed from separate bins onto a conveyor belt. But not just randomly. The whole process is controlled by a computer. An operator in a control booth inputs the exact recipe for the asphalt. Depending on where it's going to be used, a busy highway or a quiet side street, the recipe will be different. The computer knows exactly what percentage of large stone, medium, small, and dust is needed for the perfect mix. It's like baking a complex cake, where every gram counts. This mix of stones begins its journey up a long, inclined conveyor and enters the heart of the plant, the drying drum. This is a huge, long tube that slowly rotates, set at a slight angle. From one end, a powerful burner blasts a roaring pillar of fire inside, like a jet engine. The temperature inside hits 300 degrees Fahrenheit. The stone, slowly tumbling inside this drum, heats up, and most importantly, gets completely dried out. Moisture is the #1 enemy of good asphalt. Even a single drop of water can prevent the bitumen from sticking properly to the stone's surface. So, the stone has to be bone dry. After the drying drum, the hot, moisture-free stone is carried up by an elevator to the very top of the central tower. There, it passes through another set of screens for a final quality check on the sorting, and then falls into hot storage bins. Meanwhile, in special insulated tanks, our black glue, the bitumen, is being heated up. It's also brought to a high temperature to make it fluid and runny. And now comes the climax. The computer gives another command. A wayhopper, with incredible accuracy, measures out the required amount of hot stone of each size from the different bins. Then, a precisely measured amount of hot liquid bitumen is sprayed into this superheated stone mix. This entire mass, stone and bitumen, is dropped into a mixing chamber called a pug mill. It's like a giant kitchen mixer, but instead of whisks, it has 2 powerful shafts with metal paddles. These paddles churn the hot mass with enormous force, and in less than a minute, every single stone, every grain of sand, is coated in a thin, shiny film of black bitumen. Out of the chamber comes the finished asphalt, a uniform, steaming black mass with a characteristic oily smell. Now this hot, freshly made product needs to be stored until it's shipped out. It's lifted and dumped into special insulated storage silos. They're like giant thermoses that can keep the asphalt hot for many hours, sometimes even days. Dump trucks pull up under these silos. With a loud clang, a gate opens and several tons of hot asphalt pour into the truck's bed with a roar and a cloud of steam. The bed is always covered with a tarp to keep that precious heat in during transport to the paving site. At the construction site, the final act begins. The dump truck slowly unloads the hot mix into the hopper of a special machine, an asphalt paver. This machine, moving forward slowly, evenly spreads the asphalt over the road surface, forming a perfectly level layer of a specific thickness. At the back of the paver is a heavy, heated plate called a screed. It does the initial compaction and gives the surface its first pass of smoothness, but the asphalt is still soft and loose. To make it strong, it needs to be compacted. Right behind the paver follows a whole team of heavy road rollers. First come the large steel drum rollers, which use their immense pressure to squeeze the air out of the asphalt mix and force the stones to lock together tightly. Then, pneumatic tire rollers might be used, which knead the surface, making it even denser. And in the final stage, smooth steel drum rollers pass over it again to give the road its final, smooth finish. As the asphalt cools, the bitumen turns from a liquid back into a solid. It permanently glues all the stones together, turning the loose mix into a strong, waterproof monolith. After a few hours, the road that was recently hot and soft becomes hard and ready for traffic. And that's the whole point. From the explosion in the quarry to the heavy roller on the road, every stage of this process is designed to create a durable, reliable surface that will withstand thousands of cars every single day. Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected, with ultrasound or eddy currents, to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1,800 degrees Fahrenheit, 1,000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a micro crack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Imagine this. Hidden right under your feet could be a mountain of old car tires. You'd think it's just rubbish, left to rot in a landfill for centuries. But what if I told you that this black rubber gets a second life and becomes the foundation for modern sports stadiums? Every single football field uses up to 40,000 tires. Now, multiply that by the more than 13,000 arenas in the US alone, and you get hundreds of millions of old treads, transformed from the road into a green carpet for athletes. How exactly new life is born from dirty scraps? We're about to break it down, step by step. Stick around till the end, and you'll uncover a secret most people never even thought to look for. So today, we're heading to a cemetery. A car tire cemetery. Acres of land piled high with mountains of black rubber rings. These are the silent veterans of the road, having done their thousands of miles, now lying here, seemingly useless. But this isn't the end of their story. It's just the beginning of their amazing reincarnation. We'll follow how these worn-out, dirty pieces of rubber go through a series of brutal, yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. This is the story of how the roar of the road turns into the quiet whisper under an athlete's feet. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the US is now over 85%. That's one of the highest rates for any consumer product. That means over 250 million tires a year dodge the landfill and are sent off for a new life. Some of them are burned as highly efficient fuel, some are used in civil engineering, but a significant and growing number are turned into that very same crumb rubber. In this tire cemetery, a machine that looks like a steel Tyrannosaurus Rex is at work. This is an industrial shredder. A huge loader grabs a whole handful of old tires and dumps them into the machine's steel jaws. Inside, two massive shafts with thick, sharp hooks spin with a deafening screech. They grab the tires with relentless force and, with an incredible crack, tear them to pieces. There's nothing delicate about it. The shredder's job is simply to break the tire's integrity, turning it into rough, palm-sized chunks. At this moment, the first important liberation occurs. Inside, every tire is a steel cord, a strong frame of steel wire. As the tire is torn apart, this cord is released, turning into a shiny web of steel threads mixed with rubber chunks. This chaotic mix of rubber and steel moves along a conveyor belt. And here, a powerful, massive industrial magnet spinning above the stream of shredded material comes into play. Like a fridge magnet, but a million times stronger, it pulls all the steel threads from the rubber mass. With a screech and a clatter, the steel cord sticks to the magnet and is dropped into a separate container. This steel will later be sent off to be melted down, while our cleaned rubber continues its journey. But it's still too big and coarse. The next stop is the granulator. This is something like an angry coffee grinder the size of a car. Inside, sharp blades spin at enormous speed, chopping the large chunks into a smaller fraction, about the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire extra strength. These light, fluffy fibers need to be removed. To do this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have a clean, but still quite large material. To become the surface of a stadium, it needs to be turned into a crumb. For this, the granules are sent for final grinding, often in what are called cracker mills. These are two massive grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the tiniest particles. As a result of this process, we finally get what this was all about: crumb rubber. It's a uniform, free-flowing mass, like black caviar or coarse sand, where each particle is only a few millimeters in size. This crumb is carefully sifted to ensure a perfectly uniform size, and is packed into huge one-ton bags. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now, let's jump to the place where this black crumb will find its true calling: the construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. This isn't just a green carpet. It's a backing with long, soft polyethylene blades sticking straight up. But for now, they look sad and limp, pressed against the base. For them to stand up and look like real grass, they need support. And this is where a special machine, looking like a large fertilizer spreader, drives onto the field. A process called infill begins. First, the machine spreads a uniform layer of fine, rounded quartz sand over the entire field. It's heavy and settles right at the base of the carpet, acting as ballast to keep the turf from shifting and helping to stabilize the blades. And following the sand, our main hero is spread onto the field, the black crumb rubber. The machine distributes it just as evenly over the entire surface. And here, the main transformation happens. This crumb fills the space between the blades, forcing them to stand vertically, just like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, springy rubber particles compresses, absorbing the impact energy. It's like running on a billion tiny trampolines. This drastically reduces the strain on athletes' joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and crumb rubber and brushing them deep down to the base, making every blade stand perfectly straight. And so, when the work is done, what stands before us is a perfectly green, resilient, and safe field. And none of the players running on it might ever guess that under their feet, between the bright green blades, lie millions of particles of old car tires that have completed their epic journey from the roar of the motorway to the quiet, springy surface of a sports arena, having received a second, much nobler life. To create one standard American football or soccer field, you need, on average, between 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats up a whole mountain of rubber waste. And how many of these fields are there in the country? Right now, there are over 13,000 artificial turf fields in the US, at schools, colleges, parks, and professional arenas. And that number is growing every year. Now for some simple maths. Even if we take the minimum figure of 20,000 tires per field, it turns out that over 260 million old tires have found their new home in the surfaces of sports fields across the country. That's almost a year's supply of all the rubber scrap the country generates. Natural grass is a very fussy thing. It needs to be constantly mowed, watered, fertilized, and given time to rest. On average, a natural field can handle no more than 20 hours of play per week. And an artificial turf field, it can operate 24 hours a day, 7 days a week, in rain or shine. Now, let's talk about water. A single artificial turf field can save from 500,000 to 1 million gallons of water every year. That's the amount of water an average family uses in several years. Add to that the savings on fertilizers, pesticides, and lawnmower work, and the benefit becomes obvious. So next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves a waste problem, makes sports safer, and saves precious natural resources, one old tread at a time. Then there are two paths: either long-term dry storage in double-walled concrete containers, or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Transportation is under guard, on a special route, with an escort, GPS and mandatory, 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor-grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark grey color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part, isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid. Basically, a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. Yellowcake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellowcake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellowcake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade if you can find any. There are 2 ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video. Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material, but it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created 3 substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these 3 products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage: liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learn to obtain 3 extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet, all of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies. Every year, billions of square feet of drywall are produced worldwide. In the United States alone, over 27 billion. That's enough to lay a 3-foot wide path from the Earth to the Moon, and still have enough for halfway back. Imagine millions of tons of stone being transformed into the smooth walls of our homes. But the real secret begins where ordinary gray stone becomes a thirsty powder, a material that can miraculously turn back into stone. Watch closely. At the end, you will discover a secret that most people have never even guessed. The numbers behind drywall production in the United States are not just big, they are astronomical, and they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of drywall panels. This number is so colossal that it's hard to comprehend. Try to imagine. If you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire territory of the state of Delaware twice, and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator. The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and construction. It all begins not in a workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of a primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something like coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and in essence, it's the controlled drying of gypsum. The thing is, in the crystalline structure of natural gypsum, water molecules are locked in. For drywall to be able to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum, tilted at a slight angle. Inside this kiln, a very precise temperature is maintained, around 300 degrees Fahrenheit. The gypsum powder, slowly tumbling inside the drum, heats up, and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but to put it simply, it becomes thirsty. Now this powder, which is now called plaster of Paris or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that lies at the heart of the entire production process. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line. And now the most spectacular part begins, the creation of the sheet itself. In the workshop, there is a huge conveyor, hundreds of feet long. At its beginning stand two giant rolls of special dense paper, or paperboard. One roll is for the face side. It is perfectly smooth and white. The other is for the back side. It can be a bit darker and grayish. The ribbon from the bottom roll, the face side, is unwound and laid on the conveyor, forming an endless track. In parallel with this, in a giant mixer resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its own role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to better adhere to the paper covering, and fiberglass adds strength. This mixture, called a slurry, resembles a thick grey porridge. It is poured in a continuous stream directly onto the paper ribbon, moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded upwards, forming the sides of the future sheet. And at this moment, the second ribbon of paper from the back roll is laid on top, like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers or under a forming plate, which compress it to a precisely specified thickness, for example, ½ an inch. The newly formed, still soft and wet sheet of drywall continues its journey on a very long conveyor, which is called the setting line. Its length can reach several hundred feet. As the sheet slowly moves, a real miracle happens inside it. The gypsum powder reacts with water. The rehydration reaction takes place. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt, and at the right moment makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very wet. They contain excess water that did not take part in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most large-scale structure in the factory, a multi-level drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is controlled very carefully. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer, the product we are familiar with appears, a perfectly dry, light, and strong sheet of drywall. But this is not the end. The final stage is finishing. Two finished sheets are stacked face to face. Their edges are perfectly trimmed to be even and clean. A paper tape with information about the manufacturer and product type is glued to the ends. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even piles on pallets. Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will travel to construction sites to become part of someone's home, having transformed from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is on the rise, people actively build new houses and renovate old ones, and the demand for drywall skyrockets. The factories that produce this product operate at full capacity, and the flow of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall manufacturing plants are located throughout the country to be closer to large construction markets, the mining of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa.